In this chapter, we will look at some extensions of the belief propagation algorithm covered in the previous chapter in order to deal with more general inference problems. To recap, belief propagation is an algorithm that is used to compute marginal distributions of variables in a probabilistic graphical model efficiently by leveraging the structure of the graph. It consists of a series of message passing steps where information is exchanged between neighboring nodes to update the belief of each node's marginal probabilities. The message from an arbitrary node j to I takes this particular form, where the total message received by node j is passed on to node I by filtering it through the pairwise potential between I and j. The state is then updated according to this formula, where all the received messages are aggregated. For the algorithm to be exact, we assume that the graph is tree structured, and in this case, a single message passing sweep leads to convergence, and we obtain exactly the marginals at every node. While this algorithm is efficient and gives exact solutions, it is quite limiting since in practice we often encounter graphical models where the underlying graph topology is not a tree, and moreover the states may be continuous instead of discrete. In the next sections, we will look at extensions of the belief propagation algorithm to deal with these more general settings. For the first extension, we will consider the case when the states are continuous random variables instead of discrete. Extending the belief propagation algorithm to this case is straightforward, where we just replace a sum in the message update step by an integral, since the integral is a continuous limit of the sum operation. The state update step in the continuous case is exactly the same as in the discrete case. While this is a straightforward extension, unlike the sum, the integral is generally intractable, especially in high-dimensional settings, which makes exact inference impossible, except in some cases. A common setting where exact inference is possible is when all the factors in messages are Gaussian, in which case we have the Gaussian belief propagation algorithm. Exact computation in Gaussian belief propagation is made possible by two key properties of Gaussians. The first is that the product of two Gaussian random variables yields another Gaussian, where the means and variances are related together in the following closed form expression. This allows us to compute all products in our message passing update rules in closed form, provided that all the terms involved are Gaussians. We can set the potentials to be Gaussian, as this is a modeling choice, but we need to also ensure that the messages obtained by this update rule are also Gaussian for this to hold recursively. We will see that this indeed holds true from our next property, but for now let us assume that these are all Gaussian, so we can replace the product by a single Gaussian as follows. The next important property of Gaussians is the following, where the integral of a specific product of Gaussians is Gaussian. Here we have two scenarios. In both cases, the first term is a Gaussian in the variable x centered around a linear mapping of another variable x prime with covariance r. Now the two scenarios arise depending on whether the second term is a Gaussian in the variable x prime and the integral is over x prime, or the second term is a Gaussian in the variable x and the integral is over x. In both cases, we have closed form expressions for the integrals, and both of which are Gaussian. This is useful when computing the message update step in closed form, when the pairwise potential is chosen to be of the form given above. In this case, this property enables us to compute this integral exactly, giving us a Gaussian. Thus, we can iterate this procedure, sending messages from the leaf nodes to the root and back, where at each step, computations can be performed exactly to yield Gaussian messages and states. As a common setting where Gaussian belief propagation is applied in the real world, we consider the problem of linear time series modeling, where the goal is to infer a sequence of latent states z1 to zn from a sequence of observations x1 to xn of the states. For example, the z variables might represent the position and velocity of an aircraft, and the x's might represent partial and noisy measurements of their positions. We assume that this is modeled by a linear state space model, which is given as follows, where the latent vectors z are assumed to evolve according to a linear dynamical system perturbed by noise, where M here is a matrix, and the epsilons are IID Gaussian random variable with mean 0 and covariance q. The observation vector x is also assumed to be a linear function of z, again perturbed by IID Gaussian random variable with covariance r. Now this system can be re-expressed in terms of conditional distributions, where the probability of zn plus 1 given zn is a Gaussian centered at mzn with covariance q, and the probability of the observation xn given the latent state zn is a Gaussian centered around hzn with covariance r. We can thus represent this as a factor graph, where we have factors between two consecutive latent states z, and factors between the latent and observed states. Now, choosing the final latent state to be the root node, then the corresponding leaf node is the initial state. If we then run a forward sweep of belief propagation from the leaf node up to the root node, then this yields the celebrated common filter algorithm, which computes the probability of the latent states Zn given all observations up to the current time. So in this example, it will compute the probability of Z1 given x1, Z2 given x1 and x2, Z3 given x1, x2, and x3, and so on. On the other hand, running a full belief propagation sweep where we go from the leaf nodes to the root node and back to the leaf node yields the Rauch-Tong-Striebel smoother, which computes the probability of latent states, for example, Z1, conditioned on all the observations from x1 to x4. Next, we look at the max product algorithm used to find the mode, or in other words, the most likely state in a given probabilistic graphical model. This proceeds by simply replacing the sum, or integral in the continuous case, by a max operator in the message update step of belief propagation. As usual, we iterate this process going from the leaf nodes up to the root node. On the leaf nodes, we ignore this product term here, as there are no descendants from which it can receive messages. To see in details how we computed these messages, let's consider the message that is sent from node x3 to x2. We first compute this product, which gives us a function in both variables x2 and x3. Now, since in this example we're considering the discrete case with 3 total states, this function can be represented as a 3x3 matrix as follows. Here the rows represent the variable x2, and the columns represent the variable x3. Now, in accordance with this formula, we simply pick out the maximal value of each row to yield this message. Once we computed all the messages, we can compute the maximal probability attained by this model by selecting the maximal value of the product of all messages arriving at the root node. In this case, we have chosen the variable x1 to be a root node, and since there is only one message arriving at this node, the maximal probability is given by this message at the second state. Note that for it to be a valid probability, we normalize this by a constant z, which can be computed by running the standard belief propagation algorithm in parallel to the max product algorithm. Now we have computed the maximal probability attained by this model, but we still don't know what the most likely state is, which gave rise to this maximal probability. For this, we do a search for the most likely state, going from the root node back to the leaf nodes, using a procedure known as backtracking. To initiate this procedure, we first find the state at the root node, which gave rise to the maximal probability. In this case, we saw that the second state gave rise to the maximal probability, so we set the most likely state at node x1 to be state 2. Next, we iteratively perform the following operation from the root node back to the leaf nodes to find the remaining components of the mode. For example, if we wanted to compute the most likely state at node x2, we again compute this product, which yields a matrix, and restrict our attention to the row corresponding to the most likely state at node x1, which in this case is 2. The most likely state at node x2 is then given by the state which gave rise to the maximal probability within this row. We see that in this case, this is the third state. So we set the most likely state at x2 to be state 3. In a similar fashion, we continue this process all the way down to the leaf nodes to find the most likely state of the probabilistic graphical model. In this example, we found the most likely state is given by the configuration 2, 3, 2, 2, 3, 3, 3. Again, you can find the implementation of this example in my GitHub for more details. The final extension we will consider is when the underlying structure of the probabilistic graphical model is a polytree and beyond. We recall that a polytree is a directed tree. That is, they have the structure of a tree, but with edges that are directed. The slight inconvenience with polytrees is that when represented as a Markov random field, then they are no longer necessarily trees, since when the graph contains a collider, then by moralization, this leads to an extra link between the parent nodes. Likewise, when we represent it as a factor graph, then we see that the factors are no longer pairwise, which was key to simplifying the analysis on trees. To accommodate for these factors that are not pairwise, first we recall our message passing updates on trees. We focus on the message update step in particular and break it down into two sub-steps. The first step is called the variable to factor message, which is highlighted here in blue, and plays the role of aggregating all incoming messages to the source node xj to be passed through the pairwise factor. The second step is called a factor to variable message, highlighted here in orange, which filters the variable to factor message through the pairwise potential and converting it into a function in the target variable xi. We see that this result is equivalent to the message sent from node j to I by simply plugging in the expression for the variable to factor message here. Now we can extend the belief propagation algorithm to polytrees, where we have factors that are not necessarily pairwise. To update the states of node xi in this diagram, we again compute messages going into this node, which is computed in a two-step procedure. The first step is to compute the variable to factor message, highlighted here in blue, which are simply aggregations of all incoming messages to the node xj's, which is highlighted here in gold. The second step is to compute the factor to variable message, which is highlighted here in orange, which filters all the variable to factor messages through the factor node f to produce a function of only the variable xi. Once all factor to variable messages coming into node xi is computed, we can compute its state by aggregating them, as usual. As with tree-structured graphs, we can get exact solutions by starting the algorithm on the leaf nodes, propagating messages up to the root node, and then back to the leaf nodes to compute all the marginals on polytrees. In fact, we can apply the same philosophy to deal with more general graphs that contain loops, yielding an algorithm known as loopy belief propagation, or LBP for short. We use the same update formulas as in the polytree setting in order to update the messages and the states. However, since in general graphs, there is no notion of root and leaf nodes, it is not clear how to initiate the algorithm. For this, a standard technique is to start off the algorithm by initially setting all the variable to factor nodes to the constant function 1. This is then passed through the formula to compute the factor to variable message, which is then passed through the formula to compute the variable to factor message, and then back again. And the cycle continues, yielding an iterative algorithm. We note that using this approach, we can opt to run the algorithm in parallel to speed up the computation, where we first compute all the factor to variable messages in parallel, then compute all the variable to factor messages in parallel, and so on and so forth. This is called the flooding schedule. We now make some comments regarding the loopy belief propagation algorithm. Firstly, It is known that loopy belief propagation does not have any convergence guarantee and can only give approximations to the true marginal distributions. However, when it does converge, the obtained results are usually good. The condition for when loopy belief propagation does or does not converge depends on the structure of the graph. So for example, convergence is usually seen on graphs with sparse connectivity, or when the loops, when they're present, span multiple nodes. Now, as we discussed earlier, when the graph is tree structured or polytree structured, then convergence is guaranteed and we can get exact solutions upon propagating messages from the leaf node to the root node and then back to the leaf nodes. There are other algorithms to compute marginals in general graphs, and the most famous perhaps is the expectation propagation algorithm. This is a variational inference algorithm where intractable distributions, well in this case the marginals, are approximated by a product of simpler ones. Here, approximate refers to finding distributions that is close to the true marginal in the sense of the Kullback-Leibler divergence. It is shown that a particular formulation of expectation propagation when applied to graphical models becomes equivalent to loopy belief propagation. Thus, we can view it as a generalization of LBP. Finally, we note that loopy belief propagation has an associated cost function known as the Bethe free energy, where minimizing the Bethe free energy leads to a fixed point of LBP. Hence, one can view loopy belief propagation as an algorithm that tries to minimize the Bethe free energy, which justifies their use from a mathematical standpoint. Finally, we provide some references to study the algorithms presented in this chapter in more details. As usual, the book by Bishop provides details on all the extensions considered here. In particular, extensions to the loopy setting, the max product algorithm, and their relation to filtering or smoothing algorithms in the time series setting. The second and fifth source provides theoretical details and motivations on the loopy belief propagation algorithm. For more details on the Gaussian belief propagation, the third source provides a fun, interactive interface to understand the algorithm better, as well as giving us a peek into its applications. And the fourth source introduces the expectation propagation algorithm, which generalizes the loopy belief propagation algorithm, and has seen many important use cases since its introduction.